o'clock now, so we can go ahead and get started. So Orhan and Philip and Rajiv are gonna be talking today. We do have some remote presenters as well, so we'll have them join in a second, but they're gonna be sharing about unstructured grid visualization.
So my name is Orhan. I am from the UXarray team as part of CISL, TDD, West under NSF. So today, as Tegan just introduced, we will be talking about unstructured grid visualization of ours, which will be using our software tool, which is called UXarray. With me, I will have two virtual presenters. Philip is also from the GeoGet team, and Philip is working on UXarray with a lot of visualization functions and data analysis function implementation. And also Rajiv, I can just show their name from here. Philip will be with us today over the Zoom call, and also Rajiv is joining us today from Argonne National Lab. Rajiv has also been in the UXarray implementation development efforts from the inception of the tool. And this is kind of a partnership between DOA's SEEDS project and NSF-MCAR's project RightGene, which created the software tool UXarray. So what is the motivation of today? So first, we will be using this cookbook, which is called Unstructured Grid Visualization Cookbook. Just a really quick information about what this material is and where it stands. So you can see Projectpedia, and if you check the cookbooks, there are a lot of them in the cookbook gallery of Projectpedia. Not only the material of today's, but you can find a lot of things in the geoscience and earth science, earth system science, data analysis and visualization efforts. Today, we will be using our unstructured grid visualization cookbook here, as I mentioned. And we have a binder option if you would like to follow along with us, or if you were able to get a local configuration in your local device up and running before this event. So you should also, you can also be doing that through the device. I had already started spinning up my binder instance, but in the meantime, we will be good with our existing rendered cookbook. So after this introduction and motivation, so this cookbook is dedicated to the visualization functionalities of UXarray. UXarray is dedicated to data analysis and visualization of unstructured grids from different model outputs such as MPAD, MSE, and others. But today we will be focusing on only the visualization aspects of UXarray. And the structure of this tutorial today is going to be first introduction about, in general, what is unstructured grids, what data and grid formats you could encounter with unstructured grids, and data structures and data mapping that we are using in UXarray in the development parts of the things. Then Philip is going to be covering the methods and libraries for unstructured grid data analysis and visualization purposes. Then we will dive deeper into how our UXarray tool can be used for data analysis and visualization. As part of today, we will be again focusing on the visualization aspect. One last thing before I leave it to Rajiv for the unstructured grid introduction. Anyway, we can catch that later. So Rajiv, are you in the Zoom call?
He's having some issues with the password. It's still the same one. I mean, I can say it over here because everyone knows it. It's still ESDS 123 exclamation point, right?
Yes.
Yeah. Okay. I can start the way, Philip.
Yeah, go ahead. I'll message him on Slack and try and get him in.
Okay. Yeah. Wonderful. And okay. In the meantime, I remembered what I was gonna talk about. So UXarray, the name suggests unstructured grids X array. So, and as the name suggests, we from a development standpoint, we are inheriting from XArray, but on top of the XArray, which is dedicated to structured grids, we are introducing the data analysis and visualization functions that would allow us to first recognize multiple grid formats and two, perform our visualization and data analysis functions. And starting with the unstructured grids overview, I would like to first introduce why unstructured grids can be important. So
Also, Rajiv is here, by the way, Orhan.
okay,
Just letting you know.
that's great timing. So Rajiv, can you hear me?
Yes, I can hear you, Orhan. Thanks.
Great, thank you so much for joining us. And you can start sharing your screen. And we were just at the beginning of your introduction to UXarray and unstructured grids section of this tutorial. So could you just start sharing your screen and take it away from there?
Can you please link the cookbook in the chat?
Oh, yeah, sure. I will be doing that in the meantime. Rajiv, please let us know when you are able to start sharing your screen.
Yeah, give me 1 second.
This is the cookbook we are using for today.
And then I think Orhan, if you could stop sharing as well, since there's only one screen share at a time.
Should I start sharing my screen for them to? Okay, great.
I think so.
Okay. You guys see my screen?
Yeah, we can see your screen. So please go ahead.
Yeah, so I start with the overview, right? The unstructured overview. Yeah.
All the way up to wrapping up data mapping.
Yeah, sure. Yeah, so this notebook sort of tries to get into why we are doing all of this, what structured grids are, what unstructured grids are, where does UXarray fit into the picture, and then go a little bit into what some of the constructs are in UXarray and why we made the decision for things. So for structured meshes, like we use Xarray, and structured meshes typically have a format, so they're well defined by just giving, like in X direction, I have so many points, and in Y direction, I have so many points. And that typically is, in a nutshell, very lame definition of how you would define a structured grid. Whereas in an unstructured grid, the grid can be complex, and you need much more to represent those grids. So it has a uniform representation. So there are some advantages for that. Like it is very efficient with numerics when you do computation. The interpolation is very simple because it's a very structured grid. When you're handling the boundary, it becomes much simpler because you can just say that at the boundary it is inside, outside, something like that. And it is optimized for parallel computing for some cases. So here I have a small code where I show unstructured grid doesn't use any of UXarray code. This is pure Python code using Xarray, NumPy, Cartopy. So I'm saying in the lat direction, I have 20 points, long direction, 30 points. And then we are just plotting the world map as follows, sort of. So the color structure that you see here is some random temperatures that I've mapped here. So this is a structured grid example. So you see those blocks, they're all uniform. Whereas typically for doing anything complex with our heterogeneous machines and everything, we go for unstructured grids, and a lot of new simulations with this exascale project and others. There are so many unstructured grids, and there are much fewer tools to use and to manipulate and work with unstructured grid. That's how UXarray was born. So some characteristics and features of unstructured grids are basically adaptability to complex geometry. So when you have like really fine boundaries, then you can have much refined mesh in that area, and it often runs faster because in unstructured grids you have the same resolution all over. So basically, you can refine and only run like much fewer elements and be very finely resolved in the area of interest. You can represent different types of elements, so you can like make much bigger elements like a hexagon, or even higher, like more than 6 elements, more than 6 number of faces, or have triangles and squares, and they could all be mishmashed to conform to the geometry or whatever your solver takes. So this example is again without UXarray, and here we just plot the same world map with triangles, and as you can see, like they're all over the place. And so you have to store the coordinates of each node, and how the edges are formed, um, and what are the number of the faces and so on. So you have to keep all that mapping. So there's a lot more bookkeeping, but it's not that computationally expensive, and it has its advantages. So we go there. So why UXarray for unstructured grids? So UXarray is limited to our global spheric meshes on a sphere, basically for climate type applications we are working. So, and it's basically unstructured Xarray. So the language and the style of all the functions um, and how the package works is all borrowed from Xarray. So we actually extend Xarray. That is what we'll go into next. So here in a nutshell, if you see, this simplifies working with unstructured grids. The community had like a variety of tools, and each one was kind of doing their own thing. So we're trying to be an umbrella for reading, writing different formats, and also provide major operations for plotting, manipulating, and doing other things with unstructured grids. So we currently have interface for reading UGrid, MPass, script, and Exodus files. So let's take a look at how we do the data structure. So the data structure, like any Python code, you would import it as UX. And in this part, we'll kind of go on to see the data set and data array, which is the UX data set and UX data array. So these are unstructured UX array. These are Xarray data structures that we extended and called UXarray dataset and UXarray data array. So this cookbook sort of shows you how we load a mesh and a data file. So these uh, the grid and the data are two netcdf files, and just like Xarray, you would load it with ux.openGrid, and then you print the grid object. So the grid object is essentially it consists of the details of the mesh, like how many nodes it has, how many faces, edges, and lat lon of each point. Basically, not everything is shown here, but it has all the details of lat lons for each individual point. Now the grid object has like now here the launch shows the individual points. You have the entire connectivity of the mesh, just like those triangles that we saw in the previous one. You have the connectivity of all the faces. Uh, Getting more into the data set and data array structures. So when you open it as a data set where you have a grid and a data file, so this data file corresponds to every element of this grid. So then you get a data set object, and that data set object has a data variable. So this particular file has bottom depth, and the size of that is equal to the number of faces, and that consists of the depth of all of those faces. So yeah, for every dataset object, now you have a UX grid object which essentially shows you the grid. So now because you load two items, right? You load the grid and the data. So the grid object can be accessed with a UXDS dot UXgrid. In the first part of the cookbook, we just saw how you load a simple mesh by using open grid. This part we did open dataset. And let's next see the mapping part of things. So here you see like a very basic mesh, 3 hexagons essentially connected. So you have 13 nodes, 15 edges, 3 faces. You can have a variety of meshes like that. And so this has face-centered data. Here, let's say you have data on all the edges, so all the black points. So the data could be in a variety of fashion. In the previous example there, we saw that the data was on all the faces, so like A, B, C, and so on. This here is the node centered. You could even have data on the center of the edges. So currently, these are what we support. So you, again here, load it with the open data set, and then you see the variable bottom depth has a dimension of number of faces. If it was on the node, then you would have the dimension of number of nodes and so on. And you could have layers too, so that you can have multiple number of data and a 3D basically variable with time and layers to have data for all of them. So with that, next is plotting libraries, and maybe I stop sharing now.
Yep, I think I'll take over here, and then Orhan, I'll let you know when it's your turn to present.
Mhm.
You guys can still hear me fine, right?
Yeah, we can hear you very well.
Okay, perfect. Let me get my screen shared. Okay. And then if you guys can just confirm, is the size and everything good?
Yeah, everything seems good.
Okay, perfect. So thank you, Rajiv. So now we're going to move on to some more of the technical details of the actual visualization side of this cookbook. So we're going to be going over the plotting libraries in this notebook right here. So UXarray, as we can see from this really nice diagram right here, I know there's a lot right here, but let's focus on the right-hand side. So there's all of these package dependencies that we have right here. There's hollow views, data shader, spatial pandas, and matplotlib. So these dependencies are the ones we're going to be covering in this notebook. So the first stack of tools is HoloViz. So I'm not there in person, but I guess just for Orhan's sake, has anyone here used any of the HoloViz tools, whether it's HoloViews, data shader, GeoViews, spatial pandas, or hvplot? Just for the sake of later, and maybe good to know who's worked on what. So with that in mind, the main tool and stack of software that we support for visualization is HoloViz. So as I mentioned, it's a collection of libraries that provide support for rendering both vector geometries and for rasterizing those geometries, which we're going to cover in the next section. So this is crucial because, as Rajiv mentioned with unstructured grids, it's not just a basic lat-long grid. We can't just render it as a matrix. We need to actually understand the connectivity information, understand where the data is mapped to, and be able to generate a visual from that information. So a big thing about this, so for large kilometer scale unstructured meshes, the tools through HoloViews, specifically data shader, allow us to take advantage of scalability on HPC clusters and to have high performant visualizations. So HoloViews, this is kind of the core library. It supports all of the basic vector geometry, so polygons, points, edges, etc. Data shader is a library that it's also part of the HoloViz stack. It's used for performing rasterization, which I'm not going to go too much into detail of that just yet. GeoViews, you can think of it as the analog to CartoPy, but for the HoloViz stack. So it supports projections, different features such as continents or land borders, all of the stuff that you would have with CartoPy when you're using Matplotlib. And Spatial Pandas provides the data structures that are necessary for having high-performant visualizations. So specifically the geodata frame, which we're going to cover in the Polygon section. Next, we also support matplotlib. So as of right now, our matplotlib visualization functionality is not as mature as our HoloViz support. So for the rest of this notebook, we're going to be covering our HoloViz functionality, but matplotlib is something we plan and continue to aim to support in the future. So yeah, the reason we chose not to move forward with matplotlib initially was it had limited support for structured grid or unstructured grids. Really, you can plot triangles and polygons, but the performance compared to data shader specifically is significantly slower and impractical for our use case. So we'll see as well with the HoloViz tools, you can still use matplotlib as a backend, which will allow us to generate plots in the style of matplotlib. And yeah, collections and CartoPy, I think I already mentioned. These are just the matplotlib equivalents of what I already went over. Cool. So moving forward, rendering techniques. So I threw out the term vector geometries, rasterization. In this notebook right here, I'm going to discuss what those are for those that are uninformed. So yeah, since unstructured grids require significantly more overhead to actually represent the complex geometries that make up the mesh, the choice of your visualization technique is extremely important to be able to obtain accurate, but also speedy visualizations. So the first type of technique is representing each element as a vector geometry, aka a shape. So our nodes, edges, faces, all of these primitive geometries can be converted into their equivalent geometric representation for visualization. So for example, here in this little blue visual, we can see we have a mesh of hexagons here, and the hexagons are each made up of edges, which then form and come together to have our mesh. So this right here would be an example of a collection of vector polygons. Another example of vector geometry or shapes could be when you're working with CartoPy, when you have your continents, these are typically represented as shapes or geometries that are then rendered on top of your existing visual. So now real quickly, just doing a quick visual example of Shapely. So we use Shapely in the backend for like computations. We don't expose much of Shapely to the user, but it's nice for just very basic examples right here. So we can see a node is just represented in terms of its latitude and longitude points here. An edge is just two nodes connected together to form a line. And then lastly, a polygon is just a set of counterclockwise points which form together to make a closed region like this. So these three are going to be important for the UXarray visualization section. So keep these three geometries in mind because they're kind of the foundation of all of the different visualization methods that we have. And then for the last technique, rasterization. So once we have all of our vector geometries stored in some representation, instead of rendering them directly onto the screen, like in terms of their actual geometries, much of the time with your computer, really most applications, you actually raster the image or raster the geometries before rendering them. So rasterization takes these geometric representation and maps them. Is my video still sharing?
Yeah.
Okay, someone was asking me to start my video. Oh, I'll just click on it. But yeah, rasterization, as we can see from these three examples right here, it takes the geometry or points, lines, or polygons and maps them onto a matrix of pixels. So as we all know, our monitors, our laptops, when we look at something, it's essentially just a matrix of pixels. So rasterization, depending on your choice of parameters and everything, is a way of representing what these geometries are on a limited set of n by n pixels, for example. So here, when we look at that mesh that we had originally, when we rasterize it, we get these staircase patterns, the jagged edges around. This was emphasized a little bit to show like the resolution difference, but we can see here that it still represents the trends of our data, but it's not a one-to-one representation of the actual data variable. And we'll see I'm going to pass it off to Orhan in a second, but once we get to the polygon and point visualization, we'll see that this trade-off, in terms of performance and obtaining really speedy visualizations, may be worth it, and for most cases may even be necessary to obtain visuals for large, high-resolution data sets. So I will pass it off to Orhan, and he will handle the plotting API and grid topology sections.
Thanks very much, Philip. So,
Let me stop sharing.
okay. You stopped? Oops, no. Okay. You start sharing the screen again. Let's see if Finder was up. Okay, looks like. So I will be going in between the rendered HTML page and the binder, because sometimes the code is better and we can get some interactivity. Sometimes the rendered HTML page shows us some tips and hints in a better way. So let me start with the rendered page first. Now, as we have the foundational information behind what unstructured grids are, what should be done with their visualization things, like what technologies, plotting APIs could be used for that, and what we are using in UXarray, I think we can start with looking into the plotting API of UXarray one more time. First, if you are familiar with XArray, the first thing you will notice is it is really close to XArray namespacing and API. So I would like to show that from here. As Philip mentioned, this is kind of maybe much detail, but first, I would like to talk about here. As you can see, as of today, we can support UGrid, MPass, Icon, ChemSE, Script, Exodus formats already. And all of them are being represented in UXarray in a single unified format, which is very, very close, but adds some more features to UGrid conventions, if you are familiar with that as well. What we do here is, as Rajiv introduced, we have a grid object to give our data structures and knowledge about what is the underlying unstructured grid topology is looking like in this UXarray that is handled by this grid object. Oh, my cursor, okay, I don't need this. And these two, data set and data array, which are very, very close to XArray's counterpart, data set and data arrays, but these ones are knowing what is this data set or data array having as a grid topology. So what grid topology they belong to with the help of a grid object. And regarding the visualization aspects of the things, you can see, regardless of the object, it is grid or data set or data array, you have a plotting API, just like XArray provides. Grid.plot, dataset.plot, or data array.plot. And under each of them, you have specialized functionalities for visualization purposes, which wraps up under the hood all of these functionalities as Philip described. So our visualization is specialized to unstructured grids visualization. Because of that, we are providing all of these unstructured grid specific visualization functions, but under that infrastructure, we have HoloViews as the workhorse of the visualization of UXarray. And there are also these green parts, which I would really like to talk about in just a few seconds. So in addition to the visualization functions we provide out of the UXarray, we also provide some conversion functions so that if you are more interested in using your own visualization package, for example, Matplotlib, you can get an intermediate data structure out of UXarray, for example, poly collection or line collection, which are native data structures of Matplotlib. Then you can just go away from UXarray, use your own preferred visualization package. In this case, it is Matplotlib, and you can still do your visualization. But we highly recommend using the UXarray visualizations because those are first scalable, second interactive, and third we are maintaining them for most of the UXarray unstructured grid visualization purposes. After we talk about this like general diagram of our plotting API, I think we can dive into the details of these like each object's plotting API. So I would like to first start with the grid plotting. So let me just keep running my notebook here too, so that we can play with some of those codes in the real time. This is the plotting API. Okay, let's just import UXarray. And as Philip mentioned before, in most of the cases with your unstructured grid research, you have a grid topology definition file, which is most of the time a netcdf file, and also the data variables files. So as you can see here, because of that, we are most of the time using at least, reading at least two files in. One, the grid file, two or more, the data variable files, which are belonging to the grid topology that is defined in this first file. We are reading in those two files in this case. And just for the sake of what are our like grid objects and UXDS dataset objects, here they are. And for your information, each of our dataset or data array objects have their own corresponding grid object because they belong to one grid topology. Because we are using the same grid file definition here, both of these are the same grid topology. First, let's start looking into the grid plotting. This is the default plotting method for grid, which plots you the edges or like mesh structure. So you can see this is an MPass data format, grid format. So you can see most of them like uniform, like hexagonal shapes or polygons in your faces. And the default plotting method is just plotting the edges of the mesh topology. Well, so I think this is a caching problem that shouldn't be related to the tutorial itself. And I am not going to go into the details of the interactivity that would come from the HoloViz technologies, but would like to showcase really quick. You can be able to like rectangular zoom. Or just pan, or also some scroll zoom as well, which probably work with my two fingers. And these are the interactivity features coming from the HoloViz technologies we just mentioned before. Just like that, there are some more grid topology functions. For example, if you are interested in plotting the nodes instead of edges or the mesh topology, you can just call grid.plot.nodes. Or similarly, you can do a dataset grid plot as well. So this is the grid topology visualization, and we will be going into the further details of each of these functions in the next sections of this tutorial. So I will just move forward quick. Dataset and data array plotting. So assume you have a data variable of interest, which is corresponding to one grid topology, and you would like to see that in an unstructured grid structure. So this is the dataset you have. This is the data variable of interest to you, and you are just plotting that with our UXarray. here is the result. Since this is an n-pass hexagonal or primal mesh, you can see all of these cells in an hexagonal structure. I can just zoom into this one of these regions, and just like that, you can also plot the face centers of the same mesh as a point plot. And if you call the data set plot, you can currently get a warning, because for data sets, we don't have any plotting functions yet, because we are focused on the plotting functions of the data arrays. So in each data set, you may have one or multiple data variables. If you go through that data variable of interest, you should be able to run your visualization functions. But as a whole data set, we are not yet supporting any visualization functions. There are some customizations which are mostly coming from the HoloViz technology under the hood. So you can play with the figure size as expected, and also you can combine some of those plots into subplots if you are interested in maybe some comparisons of the data variables, or you can also do a single column, not side by side, but from top to bottom plotting as well. So this is a general sense of our plotting API, and from now on we will be going deeper into the details of our visualization functions. The first one is grid topology, which is also going to be covered by my shared screen. So with the grid topology, why you may use grid topology visualization? Because at any time, if you are using analyzing the unstructured grid data, you may need to know what is going on with the data, like mesh structure itself. So you can always need some grid topology visualizations, even if it is not your eventual goal, or even if it is not your actual purpose of the data analysis. So because of that, turning back to my binder instance, let's start a grid topology visualization notebook in this one. By the way, is there anyone in the room who is following along with me? Okay. From time to time, we can just get interactive and play with those codes if you want. I would like to do that on my shared screen as well. For this grid topology visualization notebook, we are going to showcase only the grid, standalone grid object visualization, because as I mentioned before, at any time, if you have a UX data array or UX dataset object, you should already have a grid object which is corresponding to that dataset or data array. So whenever you have UX data array or UX dataset, you should be able to access its grid object in as simple way as like UX dataset.grid.plot. But in this notebook, we will be just showcasing the grid standalone object itself, because the rest is the same. Let's just read in similar data formats, as you can see here. I have this is what I've already talked about, so just mentioning here. Whenever you have UX data set or UX data array, just like you can see here, you can simply access their grid object like this. And after then, it is just a grid object plotting, just like calling the plotting API, like you can see here. Or if you have a grid, like standalone grid object, you can also do that here. When can you have a standalone grid object? You may be just interested in diagnosing a grid definition file. Instead of opening dataset, you may have just created a grid object by calling open_grid through UXarray. Then you may have a standalone grid object. After then, let's turn back to the binder one more time. And let's first start with plotting the edges. And as I mentioned before, the edge structure of any unstructured grid topology shows you the actual or the closest sense of a mesh structure. Because of that, we defaulted our plotting method to plotting the edges. So as you can see here, we are calling grid.plot with a number of optional arguments we can talk about here. It is going to plot the edges instead of nodes or faces. We had talked about this before, but I have two small tips here as well. One, it says also try grid.mesh or plot.mesh and grid.plot.edge. So we can go a little bit interactively here. So in addition to this default plot here, UXgrid.plot, what I would like to do is maybe create a new cell. And instead of plotting with this default plot, I would like to do plot mesh with the exact same list of optional arguments. And this is the same. Under the hood, they are all the same functionality. And even if I called edges, it should have created the same output as well. Another tip here, there are additional optional arguments. So you can try limiting your plotting area into a region of interest to you. So you can use X limits and Y limit for that purpose. Let's just give it another try. I think we can make use of this one for that purpose. And here it is. So instead of a global map, you just created a region of interest in that map. Moving forward, turning back to HTML page, using exclude antimeridien. So antimeridional faces are common even if they are not frequent in the grid topology files. So you can have some percentage of your data, let's say 1%, maybe below 1% of your data, residing in the antimeridional zone. And you have to treat them for the best visualization outcomes. That treating requires using outside packages functionalities such as spatial pandas, and which gives you a performance bottleneck. Because of that, we just provide an optional argument that is called, one more time, the exclude antimeridien, which is true as default, as far as I can remember. So let's see. I think it should be defaulting true, but let's just give it a try to see. So this is the antimeridional mesh parts or faces excluded, and if we follow it with false, we should see some. Okay, you can see here. If we call any plotting method with antimeridional exclusion false, you can see we are treating well the antimeridional region faces, just like here. So if I zoom into this region a little bit more, you can see how we treat them well. But if I do that one more time, you please focus on this edge region. If I do that one more time to exclude instead, you can see how they are just left as is, just like here. As your data set size gets bigger and bigger, this inclusion of antimeridional faces could be really a performance bottleneck. And because of that, if you're short with your time, you would like to have some, visualization outcome, maybe just put that false and then get your plot created. Or if you have time enough, then you can just go other way.
So I see that you can exclude the faces that cross the antimeridian.
Yeah.
But if that throws that data away, right? Wouldn't you maybe want to assign the the cell to one side or the other instead of either clipping or excluding?
That's a great idea, actually. As far as I can remember, we didn't look into such an like scheme to treat in a different way. But I would like to clarify, we are not getting rid of the actual data. This is only for visualization purposes. The data still resides there for analysis purposes. You will still be using them. But for visualization, quick visualization purposes, this is kind of an optional argument. But I still like the idea for a second option there. Choosing a backend, as Philip mentioned before, we are using HoloVis, and HoloVis can use a number of backends like Bokeh, Matplotlib, and what was the third one? Philip, are you there?
Yeah, I think the third one was Plotly, but that one doesn't support most of the geometric visualizations.
We are defaulting to using a Bokeh for our purposes, but if someone is interested in using instead Matplotlib as a backend, they can still do it. So just like here. And the biggest difference, as you can see here, is since this is a Matplotlib output, you cannot see any longer the interactivity that would come with Bokeh as part of HoloVis. But under the hood, you are running Matplotlib. And again, if you don't specify this optional argument, it always defaults to Bokeh instead. For interactivity purposes, I will be faster plotting nodes. So in addition to plotting edges, you can also plot nodes. And it also gives you some like valuable information if you are interested in seeing like individual node points that comprise these face structures here. And just like the edges visualization, we have a number of different node plotting options, like node chords is also the same thing, just like this one.
There's another question
Sure.
online, asking if it's possible to plot like inside of the land areas.
Yeah.
Don't know if that would just be a different data set or if.
I think with the data sets Philip is going to use in the rest of the notebooks, we will probably be going over them. Let me just speed up my case. So we talked about these, and these are the like plotting face centers or edge centers case about your data. If your data is centralized on the edge centers or like face centers, it makes a difference between your plots. So I would really like to quickly show this plots all together. So you can diagnose your grid topology with plotting them all together. So edges here, face centers here, and the nodes also here. It could be a good, diagnosis case. I will stop at this point and leave it to Philip. And Philip, could you please let me know if you would like to share your screen again, or?
Yeah, I can go ahead and share it. All right, let me do that real quick. And yeah, just to answer the question that we had in chat. So the reason the land wasn't visible was because we were using an MPass ocean mesh. So that one already had data, like it didn't have any data over the continents. It was actually a partial coverage over the entire sphere. So that's why it was not filled in there. But moving on to polygons. So Orhan just went over visualizing the grid topology. So there was no data associated with any of those, or no data variables associated with any of those plots. For these next two sections, I'll be covering two ways of visualizing data variables that reside on unstructured grids. So this notebook right here, we'll be going over polygons. So real quick, just a summary of the two data sets we'll be using. We have one grid with a face-centered data variable. This is the one Rajiv mentioned. It's the bottom depth for each cell. And then we also have another data set, which this one is node-centered it's a node-centered data variable, and it's, I think, the velocity in the x direction of each corner node. So I'll real quickly go over the conversion methods because we're running a little bit low on time. But as Orhan and I already mentioned, the core of a lot of our visualization functionality is built around a geodata frame. So the geodata frame is a data structure from the Spatial Pandas library, which we represent each face in our mesh as a polygon. So we can see here, we have 0, 1, 2, 3, 4, all the way up to 1790. This is each of our faces represented as a polygon geometrically. So you can do this by calling your grid.toGeoDataFrame. You can also map a data variable to it. So with our data array, you can specify you want the bottom depth and you want to convert it to a geodata frame. And we can see here now we have the same geometry, but now it's mapped with a data variable. So the key thing about this is it needs to be a face-centered data variable to be able to shade in each polygon properly. So for the case of our node-centered data set, you can perform a simple nodal average, which we have the functionality for that, which takes the average of the surrounding nodes for each face and then shades it by the average of those. So we can see here, we have V1 nodal average, and those are mapped to each of the faces. So with that out of the way, we can now go over our vector polygon plots. So when you have your data array and you call plot.polygons, you get a vector plot right here. So zooming in to, let's say around here off the coast of California, we can see this is a fairly low resolution mesh, but we can see since it's an ocean mesh, it borders the continental United States and all the other continents. And zooming in indefinitely, we can see that it's plotting the vector, aka the shape of each polygon, which for a small resolution data set like this, there's really no performance issue. However, as I'll actually cover that in a second, here plotting our nodal average, this one is a global mesh. So we can see there's no continents, no masking happening. But this right here, even though it was a node-centered data variable, we were able to still plot the polygons by doing the nodal average beforehand. So this is one way of, depending on where your data is mapped to, you can still perform the visualization. So now those were the vector examples. As I mentioned, for moderately, even like medium to high resolution grids, we don't advise you to use the vector plots. We advise you to use rasterization. So we can see here the same bottom depth data variable. We can, instead of calling plot.polygon, we do plot.rasterize. And our method is polygon because we're rasterizing each polygon. And then you pass in any other keyword arguments such as width or height. Those are the same across the board. Zooming in to off the coast of California one more time, we can see that we still have the same data variable. However, now instead of plotting each of the edges geometrically, each of the faces exactly as how they are in their mathematical representation, here we're approximating them for this rendering. So we can see the staircase pattern, the jaggedness, all of that. Same thing for this one right here. It's, again, just approximating it. So this, for anyone that has worked with unstructured grids before, this may almost seem like you're regridding and then visualizing the regrid. So when I first started researching and working on visualization, that was what was commonly used by scientists and researchers. They would take their unstructured grid, regrid it to structured, and then perform their visualization. Even though this appears like that, and mathematically with rasterization, that's essentially what's happening, you don't need to change your data at all. This is all handled through the plotting and the data shader library. So you're still working with your exact same data set in unstructured grid form, but for this visualization step, it performs the rasterization. There's nothing expected of the user. Anti-meridian polygons, I will skip over this one for the sake of time. But zooming in, we can see near negative 180 longitude. Some of them were clipped, and this was just for performance. So moving on, now for this one, you can also visualize your data in terms of their points. So the thing with points is your data can either be mapped to the corner nodes, the face centers, or the edge centers, depending on what your data mapping is. We're using the data set with bottom depth, but here we have two different resolutions. We have 120 kilometers and 480 kilometers. So plotting each point, so bottom depth plot dot points, we can see here, it plots each of the points as the center of each face. So this is almost like a two-dimensional scatter plot if you think about it. Same thing can be, so you can also perform projections on these points very easily. We don't have any issues with projections because there's no connectivities. The reason there was no projections in the previous notebook was because we're currently working on getting those implemented and correctly handling all the cases with connectivities. So we can see here with an orthographic projection, each of the points are being rendered. And then here, we might not have time to get to the last notebook, but just an important takeaway. So plotting points for low compared to high resolution grids, you can see for the 120 kilometer grid, you can, because of the density of points, you can start to observe and see that the global trends of the data variable. So like if we were to compare it to the polygon, you can start to see what the bottom depth actually looks like. So here, this is where you can choose a parameter called the pixel ratio. You can think of this as increasing or decreasing the bin size, so the resolution of our rasterization. So when we lower it to 0.4, each of the blocks in our raster is going to be bigger, which means it can group more points together for the rendering. So we can see here with a pixel ratio of 0.4, it looks very jagged and low resolution, but you can start to see the global trends. And an example here, you can see near the poles, since there's a lower density of points, because our data resides on the sphere, when you map it to a 2D projection, there's less points near the north and south pole. When you choose an appropriate projection, such as the sinusoidal one here, which it's not the most pretty, but you can see it's much more evenly distributed between the regions near the equator and the regions near the poles. And then lastly here, so those were 480 kilometer and 120 kilometer examples. This right here is taken from a 3.75 kilometer mesh. So this point raster right here, it's almost indistinguishable from a polygon plot, except for the north and south poles, which is expected. But if you do a projection such as this orthographic one right here, to the naked eye, you can't even really tell this is a point raster. So yeah, that's point rasterization. I have, Orhan, do you think I have maybe like a minute or two to touch on just some key points from the final one, or? I know I want to leave some time for questions.
Yeah, we have only 2 minutes, so thank you so much, Philip.
All right, how about, so I know we have the like hour 30 after this for just group work. If anyone's interested in talking about the visualization at scale with me, I'll be there